Okay, so today we start a new chapter on differential geometry. And I will do differential geometry in not the most general way because I have to introduce a lot of stuff. But I will work with manifolds that are embedded in Euclidean space, Rn. And some might think, okay, why don't I work only with full Rn or just some open sets in some regions in Rn. But first of all, one of the benefits of using the method with the exterior algebra formulations for especially for transport phenomena is that they can be defined even on curved spaces. And the other reason is that even if you do everything on 3D regions, we have to do calculations on boundary, which are curved, the boundaries. And so we have to know what to do with those boundaries. But before defining what a manifold is, I have to introduce a little bit of topology. But anyway, let's write like something like chapter. This is new chapter for this whole week. Is differential geometry, or let's call it differential geometry. And I will start with topology in Euclidean spaces, let's say. So Euclidean spaces will be real tuples of real numbers with the Euclidean metric. So let's define first of all, what a bow is, which is the defining feature of that metric. So let n be an integer, even 0 works, but it's a strange case. R be a positive number, so it's R plus, and x is some point in Rn. We define the following. So the open bow, let's call it BR of x. So this is BR of a tuple x1 to xn. Let's say x is use this overline here, is by definition the set of the space of O y in, so y equals y1 yn in Rn, such that x1 minus y1 squared plus n minus yn squared is less than r squared. Let's put b carne, no, it doesn't matter. Okay. So this is an open bow. Closed bow is when this equality, this kind is non-strict. So let's BR x, let's put, okay, let this be some vector notation better maybe. This is the space of all y in R. It's big. So B R X is the space of all points such that their distance is less or equal than R squared. So and for let's say L bigger than 1, the n minus 1 sphere is, let's go S L X is the space for numbers such that distance to x1 is exactly R. Okay. So just for n equals 2, we get disk, open disk, closed disk, and a circle. Open disk, closed disk. Okay, let's start with n equals 1. So examples. Let's fix R to be, that doesn't matter. Okay, let R equals 1, X is n is integer and X is the 0 point. So when n equals 1, we have open interval. We have open interval, closed interval, and the open interval is -1, 1, closed interval is -1, 1, and endpoints. This is only 2 elements, -1 and 1. Okay. When n equals 2, we have open unit disk. This is unit interval. Open unit disk. So we have this thing here without the boundary. Closed unit disk. So we have with boundary. And so we have all the points in interior without the boundary and the unit circle. So we have only the boundary here without the interior. And for n equals 3, we have open bow, open unit bow. I forgot how to draw a bow. Yeah. Okay. Yeah. So all right. So we have all the interior, but without the boundary. closed unit bow. We have this time the boundary. And again with everything inside. And unit sphere. If only the boundary. This thing here, without the interior. So these are the archetypal examples in units. So the unit bow, and maybe this should be called tree bow and tree, because there is M bow in general is for general M. These are archetypal examples of open sets, but it's very often useful to work with parallel top. So let's just introduce them. Or I will call them bricks. In my code, they're called bricks as well. So let n is an integer, a1 smaller than b1 and so on, an smaller than bn are real numbers. Define the following. So define the open it's not the open n brick, or also called n parallel top. I don't know how. There is no symbol. Maybe in one of my articles I had some symbol, but I just cannot do it now. But a1 b1, the open interval, times an bn, and second the closed one, closed n brick, like all the intervals are closed. Now the boundary is a little bit problematic because it's not just taking those sets. Okay, it's not that problematic. The boundary of an n brick. So it just we take the boundary of the first part and take the product with the rest. Then unite with the boundary of the second part. So here is a closed interval, but then we have only two elements here. So and so on. So to the last thing, a1 b1 product here, an minus 1 bn minus 1 with the last one is this an bn. So let's fix everything. So let's fix everything, all of them to be zeros and ones. So n is integer, but a1 to an are, let's say, zeros or minus ones, and b1 to bn are ones. And so when n equals 1, again, we have this kind of interval, minus 1, 1. We also have a closed interval, and the boundary is minus 1, 1. Only these two elements. When n equals 2, we get a square. So we get this is the open square, the closed square for the interior. And also we have the boundary of the square without the interior. So these are squares. These are segments and their boundaries. And for 3, we have cubes or parallelopipeds in general. And here this generalized to rectangles when these are not the same. So everything in the interior without the boundary. We have here the boundary as well. And here we have, so squares or rectangles here in general. And here we have only the boundary. So we have here, 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 and the backend also cubes or parallelopipeds. Okay. Yes. Yeah. See. These are closed and these are only 2 elements. Yeah, so okay, let's so for example here we have the boundary is so boundary of unit cube. So there are 6 faces. So we have 2 which are 0 times 0, 1 times 0, 1, and 1 times this thing, 0, 1, and 1 times this thing here. We have, so what are these? These are x equals to 0. So here is x. Front and back. Front and back. Yes. Yes. So this is y. So yes. So these are. This is front, and this is back. We have 0, 1 times 0 times 0, 1, and so y is 0. What's this? This is left and 0, 1 times 1 times 0, 1. This is right. And 0, 1 times 0, 1 times only element 0. This is bottom. And 0, 1 times 0, 1 times 1. This is top. Is it right?
I think that can function the other way around. It depends on how you draw the axis.
This is x equals 0. This is x equals
Okay.
1. Yeah. So this is 0, 1. And here is 1, and here is 1. Yeah. So this is x, this is y, this is z. Okay. Okay. Everything fine so far? Okay. This is just basic shapes. Of course, there are simplices, but they are not very useful for now. It is our interior point. So let n be an integer, positive integer, maybe even plus. Yeah, it doesn't make many sense for n equals 0. M is subset of Rn, and X is element of M. We say that X is an interior point of M if there exists a bow, an open bow, or maybe an open. Equivalently, I will not an open brick and brick. Let's go with U such that X, so X is in U, which is subset of M. And so we say that U is a neighborhood. U is a neighborhood of X. So if a point contains a bow, we can put a little bit smaller brick, inscribing a brick. And if it contains a brick, we can inscribe a bow. So that's why they're equivalent. So if I have point, let's define a boundary point. We say that X is a boundary point. This is the negative boundary point. Of M if any open neighborhood of X, open neighborhood is an open set containing this thing, this point here, neighborhood of X. Contains points outside, contains points outside M. Now let's give example. So this is name. Let's give 2D example, why not? So consider first that N is the unit ball. So this is the set of points x, y in R squared, such that x squared plus y squared is less than 1. Let's draw it. So all points of M are interior points. So if I take some point here, I can draw a little circle around it that doesn't touch the boundary. So I can draw a circle here. This can be proven rigorously, but I'm not going to do that. So any point of M is interior. Of M. Let's call this M1. M2 is the closed ball. So this is the set of points such that x squared plus y squared is less than or equal to 1. Then, so we have this thing here. So if I take a point here, any kind, so we have this thing here. So if I take a point here, any kind of circle around it goes outside. So this is a boundary point. The definition is very intuitive. It's interior if it can be wholly inscribed in the set, and boundary if it touches any kind of neighborhood touches the outside. So points in the unit in the open bow. So x squared plus y squared is less than 1 are interior. And points on the unit square, points on the unit square are boundary points. That's unit circle, sorry, yeah, unit circle. So unit circle, sorry, yeah, unit circle. Are boundary points. Okay. Okay. Okay, now we just gave characterization of single points. Let's give characterization of the whole spaces. So let n is positive. If 0 also works, but let's see. Yeah, anyway. And a subset is a subset of Rn. we say a subset is a subset of Rn. We say that M is open and write it, we will add this like here. Oh. So it's a subset that is open if all points of M are interior. All points of M are interior points. For and we say that it's closed let's say CLRN if its complement is open. Maybe we can define it as a set that contains its boundary, but the standard definition is that Rn minus M is open. Okay. Yeah, here I didn't talk at all about the unit circle or unit sphere, because it's a little bit more subtle to work for non-region. So this is a 2D region in a 2D space, and a circle is some kind of 1D region in 2D spaces, and to talk about it, it's not that direct. And if Rn minus M is open, and let's give examples. So the unit bow is always open. All points are here. So BR X is open. We saw that. Now the closed bow is closed, not a surprise. So BRX is closed always. Why is that? So let's give a rationale so we have this bow here. And the outside is this thing here. So this is the outside. Like that. If I take point here, I take some point here. It cannot touch the boundary because the boundary is in the original space. We are considering the unit closed bow, so it contains its boundary. So the unit closed bow, so it contains its boundary. So the complement contains all points that are at a distance bigger than 1. So let's write this. So for instance, if n equals 2, L is 1, and x is 0, then R2 minus B0, 0 is the following, is the space xy in R squared, such that x squared plus y squared is bigger than 1. So if I take a point that is a distance bigger than 1, I can still write a small circle that leaves it also at a distance. I can write a small circle around this point that doesn't touch the initial around this point, that doesn't touch the initial closed ball. Okay. Similar closed, so three I would open, and bricks are open sets. So if you are in the interior of a square, for example, you can write a circle that also in the interior of the square, and closed, not circle, square, yes, and closed and bricks are closed sets. So if you have some closed square, so if you have some closed square, the exterior will be distinct in the green. This will be. So again, if you take some point here, you can draw a small circle around it that doesn't touch the boundary. And try to see here. Let's complement this open. Now, interesting thing. Rn is both open and closed. So Rn and the empty set, let's find there. So the empty set, you know the sign for the empty set, and Rn are both open and closed. If you take the whole space, it's open because any point has it contains all subsets, including balls. If you take the empty set, it has no points, so it's the so-called vacuously true. And the complement of the empty set is the whole set, and the complement of the whole set is the empty set. So they're complements of open sets, so they're closed. Okay. Maybe I don't know if I use them, but let's define them. So okay, so consider some space. The interior of M is the space, the set of all interior points. So this is the smallest open set containing, so it's the biggest open set containing M. And the closure is the opposite. The closure of M is the smallest, so it's the set of all boundary points, but I will frame this. The set of the smallest set, the biggest, I forgot to say open. Yeah. The smallest closed set containing containing M. So now let's give example of semi-closed or semi-open, depends on perspective interval, which is.
Sorry, should it be the biggest open set contained in there?
Contained. Yeah, absolutely right. Contained in M. So it is a subset of M, but it's the biggest one that is contained in M, and the closure is the smallest one containing M. So let's give example. M equals the semi-closed interval. So this is in R. Okay, so this is things like that. This is 0 and this is 1. What is the interior of M? So interior of M what are the interior points of this set? Is yeah, so 0 is not every point here is in the interior, but 0 is not in the interior. So this is the open interval. And the closure of I didn't define, but this is interior, this is closure. The closure of M is the smallest closed set containing. So it's the closed interval 0, 1. Okay, so far we've done regions, so subsets of Rn that are of the same dimension in some sense. Now let's talk about spaces of lower, in general, maybe that are of the same dimension in some sense. Now let's talk about spaces of lower, in general, maybe of lower dimensions and their topology. So the study of these things, open closed set, is called topology. But we cannot say anything about unit circles, unit spheres so far. So let's define relatively open set. So now take Rn. M is subset of Rn. And U is a subset of M. We say that U is open in M, maybe sometimes called relatively open. If so if there exists, let's hope I don't make a wrong definition. If there exists an open set, let's call it X. It's open set in the previous definition, such that U equals M intersection with X. Okay. Maybe can I just the same question can be said about relatively closed. So relatively closed. So closed in M. Again, if exists X such that is closed in Rn, and U equals M intersection X. So it's the same definition, but open is substituted close. Okay. Okay. It's relatively closed. So closed in M, if there exists a closed set now of Rn. Here we have an open set X. Okay. So consider n equals 2, and M is the unit circle. So n is B, sorry, S, S1. I forgot what symbol I used for the unit circle?
You didn't say the units, the symbols, but it is S1.
Yeah, so S1, this is the unit circle. So this is xy in R squared, such that x squared plus y squared is 1. X squared plus y squared is 1. Yeah. This is the unit circle. Now let's take some arc. Let's take this arc here, for example. This is, so this is 0, this is 1, and this is 1. So this is example 1. So we have U is the space xy in R squared such that xy in S1, but x and y are positive. X and y are positive. Okay. And U, so this arc here, what can I do? For example, I can take, this is just the intersection of this disk. So if I take this disk, the first sector, the first quadrant, and intersect. But I have to take a bit more. If I take a bit more, no, I'll take something like that. This set here. But without the boundary. I cannot think about explicit definition in coordinates, but so U is the set in red, is the set, the open set in red. And then not U, X, sorry, X. Let X be. Then M intersection with X is U. So it's an open set that contains all points here, but not the boundary points. So U does not contain, not U, X does not contain 0, 1, and 1, 0. Maybe in this direction, 1, 0, and 0, 1. And to have example 2, again the unit sphere, but we take now the closed so I take with the boundary. So U is now xy in S1 such that X and so xy are bigger than 0, or xy is 1, 0, or xy is 0, 1. 0, 1. Okay. Now I can take the same here, but the closed set. So I get to use. So let X be the closed set in red. And then Mx is U, therefore U is closed. I did, so here U is open in M, and here U is closed in M. Okay. Now it's time to make a break. Yes. Okay. If there are any questions, are there any questions?
I guess can a subset be open but closed in something else?
Yes, in itself. Yes, so some note M is both open and closed in itself, regardless of the type of M. So M can be non-open and non-closed. Because you take X to be the whole space.
Related to something.
Yeah.
Open is something.
Well, you can have global definition of topology, but it's very abstract and we don't need that. Okay. I'm maintaining the stream. Okay.